Hi, in this video we are going to talk about balanced binary trees, the so-called AVL trees. So let's get started. Let me tell a few words about what is the motivation behind balanced binary trees. We have been talking about linked lists. We came to the conclusion that it is quite easy to implement a linked list in Java or C++ or Python, whatever. Maybe the disadvantage of linked lists that they store lots of pointers because we have to store a reference to the next node in the linked list. And we have been discussing that ortho n, so linear time complexity, can be achieved for search operation, for example. Then we come to the conclusion that maybe we are able to reduce this ortho n linear search time complexity to logarithmic time complexity. And that's why we have been talking about binary search trees. We come to the conclusion that ortho n search complexity can be reduced to ortho log n time complexity. But it's very important that if the tree is unbalanced, that these operations will become slower and slower. And that's why balanced binary trees have came to be, such as the AVL tree or red-black tree. They are guaranteed to be balanced. And why is it good? Because ortho logarithmic n time complexity is going to be guaranteed. You may pose the question that, okay, why is it good? It's very good because it is predictable. For example, you have a software and you don't know in advance that how many users this software is going to have. For example, Facebook. If there are 10 users for Facebook, of course it doesn't matter. We could use a simple one-dimensional array as an underlying data structure and the application is going to be fine. But if we have 3 billion users, of course we have to optimize the data structure we are going to use. And it's very good, the balanced binary trees, because they are predictable. No matter what, we are going to have the logarithmic time complexity operations for searching, for insertion, for retrieving an item, and so on. So basically it is quite scalable in the sense that it doesn't matter that how many items we are going to store in this data structure, the running time will be the same. And it is a very good feature for balanced binary trees. So what's the problem with binary search trees in the main? Let's consider the situation when we would like to construct a tree from a sorted array 1, 2, 3, and 4. Okay, we consider 1, it's going to be the first vertex or the first node in our binary search tree, so it's going to be the root node. Then we have to insert 2. 2 is greater than the root node, so it's going to be the right child of the node 1. Then what about the node 3? It is greater than the root node, it is greater than the vertex 2, so it's going to be the right child of the 2. What if we would like to insert 4? Then it's going to be the right child of 3. So as you can see, the conclusion is if we construct a binary search tree from a sorted array, we are going to end up with a linked list. And what's the problem with the linked list? Then the operation is going to have ortho n, so linear time complexity, instead of the logarithmic time complexity. And this is the main disadvantage as far as binary search trees are concerned, that we could reduce the logarithmic running time to linear running time, and it's not going to be okay. Let's consider the situation, for example, Facebook. We have 3 billion users. It doesn't matter whether the search operation is going to take logarithmic time complexity or linear time complexity. Linear time complexity is way more slower than logarithmic time complexity. So we have to make sure that the search tree is going to be balanced and the logarithmic time complexity is not going to be violated. Thanks for watching.